So let's talk about the Serre Spectral sequence to finish off the course. So here's a big picture idea. From a Serre fibration, we get, which we can think of as a fiber bundle. So we've got the data of this FE to B sequence. We get a spectral sequence that goes from information from this thing on the left to this thing on the right. So what you should read this is this is the cohomology of the base with coefficients in the cohomology of the fiber. And we'll unpack exactly what that means, but essentially it's data about the base and data about the fiber going together and giving you data about the total space. Namely, its cohomology. And the kind of magical thing is that this turns out to be multiplicative. Which means that if you want to understand the ring structure on the right, we got units of ring, you can get it from the ring structure on the left. And we'll unpack this in a little bit. So first, let's maybe talk a bit about where these types of arguments come from, and then what this garbage data is that I wrote down here, how to parse this, and the nice visual way of presenting spectral sequences. Now, this won't be entirely rigorous or complete of a dive on this subject, but I want to give kind of the salient features so that you could understand a spectral sequence if they come up in your life. So the thing I want to focus on is that most spectral sequences arise from filtrations. And in fact, we already have an example of a spectral sequence that arose from filtration earlier in this class. And I think we specifically proved this last semester, but we also proved it like in the first 2 days of this semester, which we had this argument that the CW cohomology ring of a space, with some coefficients in R, was the same as the singular cohomology of X with coefficients in R, if X was a CW complex. And this argument arose from looking at the filtration on X by its skeleton. So you have this filtration, X0 into X1 into X2 into whatever, and let's just assume, I don't know, we can just filter it like this. So you have all these skeletal filtrations, and what you do is you start looking at each of these little inclusions. Let's call this I0, I1, I2, etc., etc. So you look at each of these inclusions and what they do on the long exact sequence of associated to this pair, so the twofold pair. So you kind of look at these progressive filtrations. So you say, if I look at this guy, well, the 0 skeleton and the 1 skeleton is a nice pair, so I can look at kind of the quotient, and I said, hey, that turned out to be a big wedge of cells. So it was a big wedge of S1s indexed over some alpha, right? Something like this. And the same was true when you did x2 mod x1. You got a big wedge of S2s, and the same kind of at each stage. And we noticed that these spaces have easy cohomologies that we understand. And then we figured out that we could relate these guys to each other by attaching maps. And we came to a conclusion that you could form this object that we called CW homology by modding out by these attaching maps, doing kind of like homology on the level of cells down here. Now, to know that that builds something about X, what we had to argue was that if you have attached a cell here, it's not going to change your homology for your 0 cells. So, like, once you put your 0 cells and your 1 cells on, you're never going to change your H0 terms. And once you put your 2 cells on, you're never going to change your 0 or 1 cells, and so on, or the homology in degree 0 or in degree 1. So because we have this this kind of vanishing, where when you attach a cell, it can only affect cohomology 1 degree lower, or homology 1 degree lower, we were able to argue that by doing this attaching, we kind of reassembled X. X's homology through this filtration. And now there was a diagram that shows up in this, and so I'm gonna draw that now, just to remind you of the argument. Okay, so we had a diagram that looked kind of like this, like a long zigzag, where we stitched together a bunch of long exact sequences for pairs. So here's this one, and then here's this one, and then here's this one for kind of each of these pairs. So for this pair, we got this sequence. For this pair, we got this sequence, and for the next pair, we get this sequence, and so on and so forth. And we used this type of argument to like show that the maps in the CW complex, which the attaching maps end up looking like it's a map from here to here. Do I agree with that? Yeah. So these end up looking like they are, nope. I see where it is. It's here to here. So this is the like boundary map in the cell attaching complex. So for when you're computing cellular homology. And the reason this map kind of like ended up squaring to be 0 was because it was made up of these two different pieces that stitched together. So in particular, if I draw, okay, so if you look at kind of like the next map up going into this guy, it would come from here to here. Am I going the right direction? Nope, the other way. There to there, a boundary map. And why did the square to 0 is because like when you go here and here and then here and here, this map followed by this map is part of this guy's long exact sequence, and so you end up getting that it squares to 0. So it turns out this is kind of like a basic example of a very trivial spectral sequence. In fact, this is the Atiyah-Hertzbruch spectral sequence. Atiyah-Hertzbruch. which is the spectral sequence associated to the CW complex filtration. That tells you how to relate how to go from information about, in particular, the data you're given is the fact that the cells have easy cohomology. So if you know what the cohomology of a single kind of like sphere is, and you know about all your attaching maps in your space, you can reconstruct the information about the cohomology of the whole space. And it turns out this works additionally for other cohomology theories. So you can replace ordinary cohomology with any extraordinary cohomology theory, like K-theory, KU, KO, etc. So this is very useful in those cases. It's also kind of like the basic way in which you compute in those theories. But let's talk specifically about the filtration that gives us the spectral sequences that we care about. And we're not going to derive the spectral sequence. I just want to give some indication that what's happening is something relating to a filtration. So the Serre spectral sequence is about trying to get information about the cohomology of E. So we want to get information about E. So what we want is a filtration on E that breaks E up into easier pieces, which we hope have something to do with B and F. And therefore, we can assemble into some sort of bigger cohomology story about what E is doing. And so what you do is you assume B is a CW complex. And by CW approximation, that's pretty easy to do, or you could replace it by something that looks like one. And then you take the skeletal filtration on B. And so for each skeleton, that's a pretty bad B, let's rewrite that. So for the K skeleton BK living inside of B, look at, I'm going to call this P inverse of BK. And provided you subdivide your cell structure small enough so that each of these cells is trivially covered by F, you end up with this looking like basically the cells of BK cross F. And this is where I'm going to be a little sketchy and just say that that's what it looks like. And so what you do is you use this to give you a filtration on E, because you can subdivide, I should say this. This looks like, I'm using BK for ball, which is bad. So I'll say this looks like this cross EK on each cell, or above each cell. But essentially what you're doing is you're now giving E a not quite cellular filtration, because rather than attaching cells, I'm basically telling you how to build E as a CW complex, but where your cells look like F cross the ordinary cell. So it tells you a cell structure on E where cells are copies of F cross EK. And it tells you how to glue those all together to get a big, description of E. And it's doing that by lifting the cell structure of B up to E. So you can lift the cell structure from an ordinary one on B to one where you have these kind of like crazy cells on E. And now the change is that these guys have more complicated homology than ordinary cells, because in particular, they have that copy of F in them. So the justification will be that this somehow magically lets you know that the cohomology of a single cell, so one of these like F cross EKs relative F cross its boundary, is close to, I think it's with a shift, but it's basically the cohomology of F. I think it's plus one. So, and I don't remember these details, and you don't need to either. But the point of this is you can assemble this into filtration that tells you how to build a cell structure on EK. And so you get this kind of like new filtration. So we get a filtration. And if I write EK for P inverse BK, which is like the union of all my K cells in this weird thing, I have this new thing, this new filtration, E0, living inside of E1, living inside of E2, living inside of blah, 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 which filters all of E. And I sort of understand each of these quotients, because E1 mod E0 basically looks like a big wedge sum of F's cross S1s in this case. And so these are our like new cells. So that is more or less where this story starts. And so you might want to try to do the same argument that we did before. How much more space do I have? Plenty. And say, okay, so if I understand that, and I'll write the next one in a different color, and E2 mod E1 looks like a big wedge sum of F cross S1s. So maybe I can look at my cell attaching maps. Which both involve kind of mapping S1s onto S1s. S2s. Boundary of S2s. Sorry. And I'm misspeaking because I'm trying to write at the same time. So these cell attaching maps look like I'm mapping the boundary of F cross the boundary of a disk. So a D2 to F cross, into E1. So into E1, and then I quotient by E0. So this is basically into some bunch of these F cross S1s. And so if I've named each of my little like F cross S1 cells, you might come up with some formalism to describe these cell attaching maps. Now, the issue is that when you attach these cells, F has, homology, interesting cohomology. In fact, it can have cohomology in all sorts of degrees. It could have cohomology in all degrees because F is some space, right? So when you attach these, you don't actually know that you only affect cohomology in one degree. You actually can affect cohomology in all degree. So the key point here is that at attaching cells affects cohomology in all degrees. And I'll say possibly, because it depends on F. But the crazy thing about the Serre spectral sequence is that you can keep track of kind of all these different attaching maps without really thinking about them. And even though this can affect the cohomology in all degrees, so you don't have this thing where you've attached the cells once and you're done, like you just figure out what goes on when you attach these cells and then you stop, what you can do is kind of like figure out, well, do I know how these affected the stuff in 1 dimension down? Do I know how it affected the stuff in 2 dimensions down? Do I know how it's affecting the stuff up a bunch of cells, and so on and so forth, and come to a conclusion subject to some minor hypotheses about how you can reconstruct the whole cohomology of E out of these kind of like cellular attaching maps for these F cells. Okay, so that's the motivation I want to provide on how this arises. But let's now describe some of the formalism about how you actually work with this and what sort of object this spectral sequence is, because that is in many ways much more important. So let's define a spectral sequence so we can talk about this a little bit more formally. So a homological spectral sequence is the data of a bunch of modules. The modules are have 3 indices, but you basically pick R is fixed at a single time, and you have 2 bigraded indices. You can have additional gradings and have a spectral sequence that is tri or 4-fold graded or n-graded, but most of the time you deal with these bigraded ones because they come up a lot. And so R is some positive integer, and you've got these R's for after some initial value n, which is like your first page. R is called the page index. So this is like the rth page. We'll talk about that later. So you have this data, and you also have, and P and Q vary over all of the integers. And you also have differentials that have this funny shift in degree. The key thing to notice is that the cohomological differentials map from, if you add these numbers up, d r maps from p plus q to p minus r plus r q minus 1, so that's p plus q minus 1. So it shifts the p plus q grading by minus 1. That's why it's homological, because it decreases degree by 1. Cohomological ones instead increase degree. By 1. So this p plus q is called the total degree. We define that later. So cohomological ones, just to be clear about the notation, in homological ones, the p and q indices are on the bottom, like with homology, and for cohomologically graded spectral sequences, they're up on top, like cohomology. The requirement is that the differentials have to be differentials, so they square to 0, and to go from the rth page to the r plus first page, you take homology or cohomology with respect to the differential. And this notation's like kind of painful, but the way people think about spectral sequences is you arrange all of these groups in a page. So here I've drawn a page of the spectral sequence. So this is the rth page. Sorry, the second page. I wrote E2, so this is the second page. And a lot of spectral sequences begin at either the first or second page, and then you get the subsequent pages by taking homology. So often you have a page where you know the names of all of the groups on the page, and then you run the spectral sequence by turning a crank and computing many, many homologies all over the page in order to arrive at the next page and the page after that and the page after that, out to the infinity page where there's hopefully something you want to actually compute. So the key here is I want to write what these differentials look like, and so let me scroll up so you can see. So if you write a differential, so I'm going to write a d2, then p is increasing by r in the cohomology ones. So if you start here, you would go to the right by 2, so you go 1, 2, and you go in the q direction, you go down by r, so 1, 2, plus 1 is this guy. So this would be dr for a cohomologically graded one. So let's go dr cohomological. And if you want to get the homologically graded ones, they just go exactly backwards of this. So if I put the arrow over here, that's dr for the homologically graded one. So you can double check the indices above, but they basically look like these night move arrows. So if this is a cohomologically graded spectral sequence, you'd be computing kind of like all of these differentials, like here, here, and then this guy would go over here. Yep. So, for instance, if you wanted to know what the element in E3 of 2, 1 is, and I guess I'm doing this cohomologically, so let me switch my grading. You would want to, I really should have done this homologically because I wrote all the indices homologically. I'm sorry. I always think cohomologically. The example we're going to work with is cohomologically, so let's switch to that. Then this would be equal to the kernel of each of these maps. So here's D2, here's D2. So it's the kernel of D2 going from E2 to 1 to E2 4 0, mod the image of D2 going from E2 0 2 to D2 from E lower 2 0, 2 to E lower 2 2, 1. So that's how you would find the element at that page for the E3 page, on the E3 page. So just imagine that if you knew what all of these groups are and what all these differentials are, you could do a simple homology calculation in order to compute just what your next page is, and you keep turning the crank. In practice, very often most of the elements on this page are 0, so like a lot of things become very easy to compute with. The last piece of formalism I want to mention is what multiplicative means in the context of a spectral sequence, and we are going to have a multiplicative spectral sequence. So what it means is that there's a multiplication on this page that respects degree additively. So if you have an element whose total degree is p plus q, then, and you multiply it by some other element whose total degree is p prime plus q prime, then those total degrees have to add. And they add coordinate-wise. So like x times y, if y have, or x times x prime would be in degree p plus p prime, comma, q plus q prime, if x is in p plus, comma, q, and the total degrees add. And the differential has to satisfy the standard Leibniz law, and that's all it means to be multiplicative. So, and this holds true for all the differentials on every page. So the differential of a product is dx times y plus -1 to the total degree of x times dy. So let's look at the one example we care about, which is the Serre spectral sequence. So the Serre spectral sequence, or which is often abbreviated SSS, is what you get when you fix a coefficient ring R, and then to associate to any Serre fibration E to B with fiber F, there's a multiplicative first quadrant spectral sequence. I'll mention what first quadrant means in a second. That looks like this. So in particular, this is telling you what the E2 page looks like. It says that the E2 page has, if you assume the 0th guy is degree R, so in degree 0, it is R in each case. You've got, right, R here, and then vertically this first column, how am I going to pick that? I'm going to write this. This looks like H 0 of the base with coefficients in H star of the fiber. If we suppress R, which is going to look like H star of the fiber. So you have stuff about the fiber in this direction. And this is, again, just to be clear, this is the Q direction, and this is the P direction. And down here, in this column, or in this row, you have H star of the base with coefficients in H0 of the fiber, which is just H star of the base with coefficients in R. So if you assume that both of these are, that everything is connected, which we absolutely will, you get this kind of like identification of these two rows, and then you get other stuff in this region, which is determined by, like, well, once you know what the cohomology of the fiber is, vertically, the row has to be just change coefficients for the cohomology of the base to get that stuff in the fiber. The reason this is first quadrant is because it's 0 in the other quadrants. So aside from along the 0 axis, in each one of these, 1, 2, etc. There is nothing, all of the non-zero groups in this page are in this range, and over here we have 0, and down here, and over here. So that's why it's first quadrant. And I do want to remind everyone that we get this in particular. Serre fibrations are include every fiber sequence. So F2E, 2B. And for just the advanced mention, you can actually buff this up. So you didn't have to use the homology, the Arth homology of the fiber. You can actually turn this into any generalized cohomology theory. So you can use K-theory or something like that, and then your target instead becomes A P plus Q of the total space. So you can actually use this to compute generalized cohomology theories, and in that case, it's often called the ATIA Herzbruch Serre spectral sequence, because the ATIA Herzbruch spectral sequence tells you how to compute generalized cohomology theories from their coefficient rings, and the Serre one does it for fiber sequences, and so there's some greater generality linking these things together. But in that case, you don't get that it's first quadrant, because the cohomology theories can have stuff in negative degrees, unlike ordinary cohomology theories. So if you're a generalized, it could be that, for instance, your generalized homology theory for this fiber includes some negative degree stuff. And so you could end up with a first and fourth quadrant spectral sequence, which is harder to talk about. And I haven't explained exactly what this convergence means, so let's look at one example so that we can sort of make sense of it, but I'm going to be a little wishy-washy with it because in a lot of examples that we care about, you can be very wishy-washy about what convergence means. So let's scroll down, and let's take a look at our first example. So let's take a trivial fiber bundle, i.e. a product. So let's take S2 cross S3, and let's fiber it over S2. The fiber is now S3. So in this case, we understand cohomology of each of these guys. So the cohomology ring, and let's fix R to be some ring. The cohomology ring of SK is just an exterior algebra on a generator, xk, and the degree of xk is k. So our E2 page, E lower 2 page for the spectral sequence, recall that this is HP of the base, so here of S2, with coefficients in H in the cohomology of S3 of the fiber. And so and in this case it's multiplicative as well. It's easier in multiplicative spectral sequences just to give names to your generators because you're going to talk about them. So rather than writing these groups, I'm going to write generators. So as a ring, the base, so here's my p direction, this is, in this direction, this looks like H star of S2 in the lowest degree. That's just, I've got a unit in degree 0, and it's S2, so I've got nothing here, and then I've got an X2 in degree 2. And then nothing above. All right. For the fiber, this, right, so this is now, by that same identification above, this is the cohomology of the fiber, so of S3. So I got 1, 0, 0, and X3. And then 0 is all the way up. And that's in degree 3. Nope. There we go. Okay, and now you can fill in the rest of the chart. So, for instance, this first row, I'm taking coefficients in the 0 ring, so all of these are 0. Right? Same with the second row, I get zeros. We're just going to avoid writing down zeros. And up here, all of this is also 0, right? And this guy is 0 because this row right here, this group as a group is R, or as a ring is R. So as an R module, I guess, is R. So I'm taking in this row the cohomology of S2 with R coefficients, so it should look like this row, but the multiplicative property tells me that X3 is like my unit here, so you end up getting a copy of R here, 0, R, and then zeros, but in order for it to have the correct multiplicative properties, this guy has to be X2, X3, etc. So you got zeros. So you end up with this kind of like small picture. And from Kunith, we know that the cohomology ring of S2 cross S3 is going to be an exterior algebra on X2 and X3. And that should have elements living in degree 2, 3, and 5 generators, right? So, like, what are the generators? 1, X2, X3, and X2, 3. X2, X3. And we can see those all on this page. This is the point where you look at differentials. And so, for instance, this guy X2, the place where it could have a differential is it could receive one from this group. That would be a D2. Then a D3 would be coming from there. And there's nothing there. And D4 would come from here, D5 here, and so on and so forth. So this guy, there's no differentials coming into it that are non-zero, and all of its differentials going out of it go down to where it's 0 also. So this guy here is a permanent cycle. It's always in the kernel and not in the image on every single page, both on the E2 page and E3, E4, etc. The same is true for this guy. So the D2 map would take it there, D3 would take it here, D4 would take it here, but none of those, all of those are zeros, and the same, they can't accept anything because it'd be coming from the second quadrant, and the same is also true for this last class. Can't map anywhere, can't come from anything. So all of these are permanent cycles, and the way you reconstruct this group from this chart is you look at total degrees. So you add up on these off diagonals. So you add up where P plus Q equals something, right? So equals 0 here, equals 1 here, it equals 2 on that diagonal, it equals 3 here, 4, and 5. Nice and messy. And if you check, in fact, this guy lives in total degree. Let's just say degree of 1 is 0, degree of x2 is 2, degree of x3 is 3, and degree of x2, x3 is 5. And that's exactly where they live. So x2, x3 is the only thing living in degree 5. X3 is in degree 3, x2 is in degree 2, and 1 is in degree 0. It's not, here's a warning. Reconstructing H star of E from the diagonals is an extension problem. So it turns out that these diagonals actually have to be quotients of some filtration on the right group. So, but in this case, this is some filtration where we have one group and then a bunch of zeros. And so the only way to solve that sort of extension problem is that the group is this group, and then the rest of the extensions are trivial. So it occurs in this case that you just kind of direct sum along the diagonals, but in truth, direct sums are like trivial extensions, and it could be that you have some more complicated extensions. So there is this warning about how to get back this stuff from the E infinity page, but oftentimes the E infinity page is very close to being exactly the cohomology of E, just kind of spread out over 2 dimensions. So, okay, and that's a trivial fiber bundle. So it shouldn't be too crazy that a trivial fiber bundle had no differentials in the spectral sequence coming from the fiber bundle, and therefore it was like very easy to compute. But let's do an example now where we don't know all the cohomologies involved. So the first really cool example is the path loop fibration. So if B is a based space, then you can take based paths, and so these have to start. So if you've got x0, let's call it b0. b0 in here, this is a path where gamma of 0 is b0, and this projection map here sends gamma to gamma of 1. It sends it to its endpoint. This turns out to be a Serre fibration. We proved this, actually, if you go back and check, in the first course, in the first semester. So basically, this being Serre fibration is path lifting. Yeah. So, but this is a nice. I think we proved this. But this is a really good example of a fiber bundle of a Serre fibration. So base paths are contractible. So the total space here is actually a contractible space. And that's because you can think of them as a bundle of spaghetti, and you can homotope them all down to the constant path concentrated at the base point by just slurping back along the paths, so like sucking in the spaghetti to the base point. And this contracts all of PB. But the fiber over the base point is exactly a loop. So P inverse of the base point is loops. And that's exactly this omega B stands for loops on B. And one of the things that you get from the long exact sequence associated to a fiber bundle is that pi star of loops on B is going to be just the same as pi star on B, but down a degree. So, up a degree. And you can see that from the connecting map in the long exact sequence, going from, which would go from like pi star of B to pi star minus 1 of loops B. So that's star plus 1 here to star. So the takeaway is that like loops as a functor shifts homotopy groups. So it's pretty simple on homotopy groups, but the question is, what does it do to cohomology? Or homology, but we'll check this for cohomology. And let's check in particular for, let's pick our base space to be something kind of simple. So we'll take B to be S3, and we'll try to compute the cohomology ring of loops S3. And to start with, let's do this just for rational coefficients. Okay, and this is one of the first sorts of tricks that people learn to do with the Serre spectral sequence. And so in this case, loops S3, you have this picture that loops S3, paths on S3, which is contractible, and S3 is a fiber bundle. This is not an inclusion, I just wrote that, here's P, is a fiber bundle. And what we get is then a spectral sequence from the cohomology, and let me read this, so EPQ2 is the pth homology, cohomology of the base, so that's S3. Well, that's something we understand in any coefficient system. It's very easy to change coefficients. With coefficients, though, are going to be the qth cohomology of loops S3, so a thing we don't understand rationally. And this is going to converge to the P plus Q homology of a contractible space. And we know what this is. This is trivial, except P plus Q equals 0, where there's a single copy of Q. So this means that the spectral sequence becomes a death match. So what you do is you start with the data that you know in the spectral sequence. So I'm going to write the E2 page. And the thing I know is the bottom row. So the bottom row is the cohomology of S3 with coefficients in Q, because at least loops S3 is connected. And so I'm going to, again, just write generators. So here's 1 generating a copy of Q. And then you have a 0 in degree 2, and I'm just going to call it X in degree 3. And then it's 0 above that. So I'm going to stop writing anything after that point. So here's my P direction. Here's my Q direction. And then we get to play around with this. So the moral of the story is that even though we do not know what's going on in most of this spectral sequence, we know that above, it doesn't matter what coefficient range you go into, this is always 0 above this point. So we know that the spectral sequence is only non-zero in between these two places. However, at the E infinity page, it has to be adding up to 0 on all the diagonals, and there's only one way to filter the trivial group. It's just 0, 0, 0, 0, 0. So this guy right here, he lives. But everything else on this spectral sequence page must turn into 0 eventually in cohomology. So this guy must die. So you look at it and you say, okay, there's two ways to die when you take homology. Either you aren't in the kernel, and so you look at all the maps coming out of this, and so D2 goes here, D3 goes here, D4, etc. And you say, oh, well, that's always going to 0. So X is always in the kernel. So the only way X can die is if it's the image of something. So that when you mod out by the image, it vanishes. And so you look and you say, well, where can X come from something? D2 is already mapping from here, this element, but there's no way you're going to ever get something in H1 of S3 in any coefficient system by Hurewicz theorem. So in fact, we can fill in these columns vertically. So the only things we don't really know are the entries in the 0th and 3rd column. Okay, so if you look, X can't, a D2 would come from this 0, so that one has to be the 0 map. A D3 could come from this spot right here, and a D4 and above would come from over here where it's 0. So the only thing that has to be true is that there has to be an element Y. Let's write Y in black here, and Y has to map to X by D3. It's a D3 because it goes right by 3. So now we know that, in particular, there's an element Y, which is non-zero in H upper 2 of loops S3 with coefficients in Q. There's some generator, and it generates a copy of Q. So we can actually kind of repeat the argument and observe that this guy has to be 0 in degree 1. So it has to be 0 because nothing could kill that, and it can't map anywhere to die from not living in the kernel. So this guy is also 0. And so now you kind of inductively move up on the page. Now, this is a multiplicative spectral sequence, so there's an element x times y, and by fiat, that one isn't 0, because this element right here is generating x times y generates h3 of S3 with coefficients in H2 of loops S3, coefficients in Q. And we now know that that's a copy of Q, so this is H3 S3 with coefficients in Q, which is a copy of Q. So there is this new guy X3. And so then you look at it and you say, okay, that X3 also has to die. And if you run the same differential argument, you'll see that it has to be mapped to from some element in this degree. So this ends up being a 0, and there has to be something here mapping to that guy. And now the question is that y squared, or is it something else, some new element? And you can use this to deduce the multiplicative structure of the fiber. So let's just call this guy Z. And we say, okay, so if D, and this is going to be D3, but I'm just going to use D because there's only one page where the differentials are interesting. So D3, if D of Z equals XY, well, what we know is that the question is Z equal to Y squared? Well, what would be D of Y squared? We can use the Leibniz rule to deduce that it's dy times y plus the degree minus 1 to the degree of y dy. And y goes to x, so this is xy. Degree of y is y lives in degree 2, 0, or 0, 2, so total degree 2, so that's a plus 1. So plus y times x. And so x and y, you can check that x, these have to obey the graded commutative multiplicative rule, so these commute with each other because they aren't both in odd dimensions. So this is 2xy. So it turns out that z is z is a half of y squared, because twice y squared, or z maps to 1/2 of what y squared maps to. It maps to xy. But we also know that D3 has to be an isomorphism between the source and the target in order to kill the homology groups. And so the source has to be generating a copy of Q. So maybe I could write this as something like that. And the target is mapping over there. So regardless, you get that there's another copy of Q in that degree. And you can kind of continue this inductive argument to see that there's this new element, a copy of Q here, copy of Q here, copy of Q here, and you kind of, they keep pairing up as you go up this page. So as a first full pass, you might come to the conclusion that H star of loops S3 with rational coefficients is Q when star is even, and 0 when star is odd. But we can actually do one step better if we pass to integer coefficients, and we can completely identify the cohomology of the fiber. So let's run the same argument to try to compute the cohomology of loops S3 with integer coefficients. And I'm now just going to focus in on the two columns I care about, and I know it lives in even degrees on the left, so I'm omitting all the other rows. And so what you come up with is that E2 is equal to E3 on the pages, then nothing happens when you do the differential page, and then E3 is where all the differentials have to live, because everything's in these two columns that are separated by a distance 3 apart. And then so E4 and above has to equal E infinity, which has to vanish. So let's name our elements a little more cleverly. So let y1 exist in H2 of loops S3 such that d of y1 is x. So y1 is going to live here. And my differential maps these guys. Over here, we end up with this new element. Let's just call this y1x. And then inductively, we observe that there has to be some element here mapping to y1x. I called that z before, but let's just call this y2. So let's now define yi as living in H2i of loops S3 with integer coefficients such that d of yi, y lower I, is yi minus 1 times x, which we know is a generator in the right column. So you end up with like y2x, y3x, y3, y4. Let me write these a little bit farther apart. y5, y6, y7, y8, y9, y... and these differentials are all isomorphisms between copies of z. So here's how they kind of pair up. y4x, never really get this, y5x, y6x, etc., going up. And since all of these maps are isomorphisms, and they all go down right like this, you want to sort out kind of like what is the relationship between y1, y2, y3, etc. In particular, the claim is that like each of these guys should have something to do with y1. And it turns out the correct structure is that this is an exterior algebra, or sorry, a divided power algebra on this single generator, y1. So, and you get this from the Leibniz rule. So the claim is that H upper star of loops S3 with integer coefficients is a divided power algebra on y1. Which you'll recall means that multiplication behaves like these are supposed to be. So yk is supposed to be equal to if like y is y1, y to the k over k factorial, even though we can't divide by k factorial. And this gives you the correct multiplicative rule using binomial theorems. So in particular, yj multiplies to give you I plus j, choose I, y, I plus j in this binomial theorem. And we get this sort of, like, the place that this rule comes from is exactly just the Leibniz rule. So if you try to compute the differential on y1 to the nth power in whatever degree it is, you're going to end up with d of y1 y to the n minus 1 plus, and then the degree of y1 is 2, so because it's an even generator, I get just a normal plus. y1 times, and then inductively, n minus 1 factorial d y n minus 1. And you can check that we actually computed this in the first case for y1 and y2 in the last page. And then some basic rearrangement. Now this is x y1 to the n minus 1 plus y1 n minus 1 factorial, and d of yn minus 1 is x times yn minus 2. And so you end up with a bunch of stuff. Let's see, what is this? This is x times n minus 1 factorial y1 to the n minus 1 plus y plus n minus 1 times yn minus 1 x the n minus 1 factorial by factoring, and then yeah, this looks like n factorial x y n minus 1. So you get to conclude that the differential kind of forces these sorts of rules on the interaction between your generators, which I think shows how powerful these multiplicative spectral sequences can be, because I was able to sort out my entire multiplicative structure on all these generators in these different degrees just from, like, the force of the Leibniz rule and the fact that I know these groups are just copies of Z. So yeah, pretty useful. So we can also use this path loop fibration to compute cohomology of Eilenberg-MacLane spaces, which is interesting and fun. For example, if you take B to be K, G, N, then loops on B is a K, G, N minus 1, because all your homotopy groups have been shifted down by 1. So you end up with a fiber sequence that looks like K, G, N minus 1 to something intractable to K, G, N. And for instance, even for G equals Z, this is interesting to compute and hard. This gives you a tool to inductively compute the cohomology of Eilenberg-MacLane spaces with some coefficient ring that you care about. So for instance, if we try to do this integrally, which is often the hardest for the integers, we could start with the fact that I know k, z, 1 is S1, and k, z, 2 is CP infinity, and I understand both of their cohomology rings very well, and try to compute the cohomology of KZ3 and see what you get. But let's first look at the one for CP infinity. So notice that the induction is kind of going up as you go to the right. So in this case, the spectral sequence looks like for S1, you've got a generator in degree 1. And for CP infinity, we know we have a polynomial algebra. In degree 2, 4, 6, etc. Right? So this is giving us a polynomial algebra. Let's just write that as z adjoin y, degree of y is 2. And this is giving me an exterior algebra on x. And degree x is 1. And what you can check the degrees, and since everything needs to die in this page, you can learn that x had better go to y, and then as you kind of fill in the page, you discover, oh, there has to be an element xy here, there has to be an element xy squared by multiplicativity, xy cubed, etc. And knowing the differential dx is y is going to imply by Leibniz that dxy is y squared, because also dy is 0. So, and so on and so forth. So, in fact, dx y to the n is going to be y to the n plus 1. And so you end up with all of these isomorphisms. So I'm just going to write 1 to tell you it's taking you to 1 times the target. And this is what the spectral sequence looks like. And so you can see how things are pairing up to die by the infinity page. However, as soon as you go up 1 degree to try to compute the cohomology of KZ3, things get a little worse. So let's just be careful. So here we're going from CP infinity point to whatever KZ3 is. I know it's possible to give that some manifold description, but it's going to be bad enough already. So now our fiber looks like it's got generator 1. Let's use the same notation as last time. So y in degree 2, y squared in degree 4, y cubed in degree 6, 8, y to the 4th. And in order for things to die, inductively down here, the first thing that you'll discover is the first element that's non-trivial is there has to be something in degrees 3, let's call it z, with a differential pairing these guys. And let me draw my differentials into color. So the first thing you'll get is that d of y has to be z. And the degree of z is 3 in the cohomology of KZ3 with integers. So then inductively you might start filling these things vertically, so you know there needs to be an element yz here, y squared z, y cubed z, y to the 4th z. And using the same argument that we gave last time for computing differentials in the divided power algebra, you'll see that this map is multiplication by 2, and this map is multiplication by 3 factorial. So this is really 2 factorial and 1 factorial. This is a 4 factorial. This is a 5 factorial, etc. So these don't on the nose hit the generators. So in particular, this thing would live under this homology on, let's see what this, on the 3rd page of the spectral sequence. So there actually has to be something that this is mapping to such that the kernel is generated by 2yz. And we can now check, well, what's d of y comma z? Oh, d of y z? Well, it has to be z times z plus 0, so it's z squared. And so, oh, I guess we can name that target z squared. However, I need to know that the kernel of the map taking yz to z squared is generated by 2yz, which tells you that 2z squared is 0 in the target ring, or in the target module. So you have z squared mod 2z squared. And so this is another way of saying the groups that you're getting down here, you got a z in this degree, you get a z in this degree, but then you're going to get a z mod 2 in this degree, and that's in degree 6. In between, you're getting zeros by the vanishing property. And so the thing I'm drawing down here is, this is a picture of what the cohomology of kz3 with integer coefficients has to look like. And you say, okay, great, so let's inductively start filling in more information, because I've now dealt with this kind of like diagonal sequence of differentials, but then I go up a degree and I realize, oh, this one is having the same problem 3 times it has an issue. So you say, hey, maybe multiplicativity fixes this. So in this degree right here, I'll have yz squared, but I'm also going to remind myself that this mods out by 2yz squared. So 2yz squared vanishes because it vanishes in the bottom row. So, and you can just check to see like, hey, does our life save us? But d of y squared z is going to be d of y squared times z, and then plus 0, because d of z is 0. d of y squared is y z, and so it's yz z, which is yz squared. So, in fact, this map, let's, I guess I'm drawing these ones as green. So this is 1. This sends that guy to the target. However, that's not enough, right? So we need to add, oh, oops, sorry, I just absolutely made a mistake. So I made it down here. So y squared doesn't go to yz, it goes to 2 factorial yz. So I'm getting 2 yz squared, which means that this map is 0. So in fact, or it hits 0 times yz squared. But I do know that it needs to hit something at some point. But I know it's not going to hit yz squared. So the next possible place where this differential could hit something is going to be down in the bottom row. And if you work it out, so let me draw a box here. Y squared z lives in total dimension 7. So since the differential increases degree by 1, over here in degree 8, there has to be some new generator. And let's just call it W, such that y squared z hits W in that degree. And inductively, since we're kind of like, we started with knowing what this is, and then knowing what this is, and then now we know what this is, now we're kind of at the point where we know what this is, and now we're forcing this to be something. And so you keep kind of like getting an extra square here, and then a square here, and then a square here, and then you figure out what the next square is, and you fill in. So you end up with a W, and because 6 times this has to generate the target, you end up with the relationship that 6W has to vanish in the target. So, which doesn't, yeah. So that's how you start getting these types of calculations. And you could now keep percolating up and see kind of like where you're getting other complicated information. Um, and some things are kind of nice. So in particular, like if you go vertically up this column, you'll see that this next element is y squared, z squared mod 2, y squared, z squared. And for the same reason as down below, since this differential would take value in 3 factorial times the target, that divides 2, so you're getting a 0. So in fact, all of these differentials here are 0, which is great. So you just know that now these elements have to persist to something farther than that row. They have to go to something over here or down on the bottom row. But just to point out one more class. So for instance, this guy here now looks like it's gonna persist to infinity because it's not in the image of anything. So the next place it has to it would have to take a value in something on the bottom line, on the bottom row. Its total degree is 8, so it would have to have some target, let's call it A, living in degree 9, that this hits, and it would have to be an isomorphism, so you have to have A mod 2A as a target there. And so you can start picking out different generators, figuring out things. There do end up being some patterns, so you can work out that, like, but they're not they're not all great. So you can see really rapidly that this cohomology explodes. It like gets really complicated very quickly. But if you wanted to compute it rationally, you can see that it disappears above this degree rationally. So the only copy of z that you can have is this one right here, in degree 3. And the reason for that is because rationally, this spectral sequence, the 1, the 2, the 3, the 4, the 5, those are all isomorphisms between these groups if I can divide by 3, by 4, by 5, by all the positive integers. So rationally, you don't have to do this garbage that we started doing with denominators in the 6th column and the 8th column and the 9th column and so on and so forth. So like, as a conclusion, you could maybe draw from this that we know some things about this guy's cohomology, and we know that this is only torsion above degree star equals 3. And I think that's maybe a good space to stop. There's a lot of different calculations you can try running at this point. For instance, you can try to compute the unitary group. So maybe like a good next example would be you have an action of the unitary group on S2n minus 1 through the complex action. So embed S2n minus 1 into Cn and act. The stabilizer of this action is Un minus 1. So you end up with a fiber sequence that looks like Un minus 1 to Un to S2 to n minus 1. And you can use this to compute inductively the cohomology of the unitary group, but you have to know things about the convergence, because you certainly know what this is, and inductively you can figure out what this is, and so then you can get the middle group using the Serre spectral sequence. I'm going to stop there. It's a good kind of general introduction to see how this machinery works. Oftentimes when people see it for the first time, it is just a nightmare, but it's worth seeing kind of like how people actually manipulate the objects on the page and what differentials look like, because the notation is cumbersome, but the conclusions are interesting. I will point out, maybe it's the last conclusion, all of these arguments about what the differentials were didn't really, like, we didn't go back to the fiber sequence. We're just using the existence of the spectral sequence to know what they are. If you have a spectral sequence where you actually need to know what a differential is and you can't conclude it for algebraic reasons, like what it's doing, things get a lot harder. And you have to know some topology. You have to know how the spectral sequence is constructed, and how these differentials arise. And that's harder. It's more advanced spectral sequence wizardry. So, word to the wise. Bye.